we have a lot of customers that are using GLD, and it seems to be a very popular topic these days to ask questions about, well, okay, we've got a customer that's come to us with a geothermal system that is failing or not performing as expected, and what can we do? And so we thought that would be a good topic for our users, and we've invited Terry Proffer to give a presentation for us today and again on December 3rd. And just a little background for Terry, if I can take the liberty of telling you a little bit about him. He's been involved in the geothermal industry for a lot of years, and previously Terry was a geologist, and so he knows the business from the perspective of the geothermal as well as the conditions that drillers are going to face. His experience includes heat loss analysis, loop design. He's done thermal conductivity testing, and has done over 500, he's trained over 500 contractors and engineers through IGSBA as a trainer. And Terry's one of the few practicing certified geo-exchange designers in Colorado. He's a factory certified Climate Master trainer, member of the Rocky Mountain ASHRAE branch. And Terry's going to do a presentation today which is going to involve an overview of what to look at first when you're presented with this type of a problem. And then on December 3rd, we're actually going to spend the entire presentation using GLD to work on a couple example systems. So with that, I'm going to turn it over to Terry.
Well, good morning or good afternoon, depending on your time zone, everyone. And I'm going to unmute all here. We were having some conflict, so we'll see if that'll work now. And assume everyone can hear me okay.
Terry, people can individually unmute as they need, so maybe you should just mute everybody from this point, because we've had problems in the past. There we go. We've had problems in the past with everything from music on hold to people coming in and out of rooms. So if you have a question, you can certainly raise your hand or unmute your mic and ask the question at any time. So, okay, Terry.
Okay, thank you. Well, welcome all. What we're going to do is go through some examples for some forensics efforts that, and what I've done is selected 3 projects where we've used GLD to assist in the evaluation of why we had problematic systems. And anyways, it's a pretty good tool because you can use GLD to reverse engineer a ground loop if you have all of the preliminary design inputs, or if you have to remanufacture them yourselves. So that will get started. We're going to focus on closed loop ground heat exchangers, although we do a lot of forensics for open loop systems as well. But since GLD is a closed loop design tool, that's what we're going to focus on. What we're going to look at is using GLD to define the problems, and then use GLD to help sort out what the solutions might be. And just want to make the point, probably one of the biggest reasons we see with problematic or failed ground source heat pump systems is either design and or installation, where people rely on rule of thumb factors. And I do like GLD's motto for systems that work by design, not by accident, because unfortunately I believe that's our biggest issue to growing the ground source heat pump industry is the rule of thumb attitude by a lot of folks. So hopefully we can show you the results of some of that. Okay, one of the things, however, that we often find with a lot of closed loop systems that are problematic, one of the first things that is done, people want to blame the ground loop. What we have actually found is a large percentage of these problematic systems are not the ground loop itself, but everything from miscontrolling of the system to maybe taking a shortcut on the outside air strategies, all kinds of things. So what I would encourage you to do before you get into looking at the ground loop as the issue is look at everything on the surface, everything from controls to piping. Do they even have the right heat pump schedule? We've seen, for extended range operation, we've seen people put in water source heat pumps that were not designed for extended range, and that was part of the problem to begin with. So a lot of times it's not even the ground loop. So what you want to do is you want to eliminate the other potential impacts on a forensics effort before you get to the ground loop if it's not really obvious that the ground loop's the problem. I'd say probably the biggest problem we see on a lot of bad problematic systems is improper sequence of operation of the controls. Give you an example, we see a lot of outside air issues where the energy recovery ventilation unit is in economizer mode 24/7 regardless of the outside air temperature. So that obviously puts a load on the ground loop that was never intended. So it's a lot of little things that you have to identify before you get to the ground loop a lot of times. We also like to go through and sample the heat pumps if it's a distributed package system or a central heat pump system. We'll functional performance test a sample of the heat pumps to help get an idea of where the problems may lie. For example, if you're finding that flow rates are way too low for the system, that the jumper wire for extended range operation is not cut to allow it to operate at extended range. A lot of little simple things to look at first. But a functional performance test also reveals problems on sequence of operation and how the system is controlled. Because if you cannot manage a functional performance test, that's probably part of the problem right there. We've also seen issues where on three-phase heat pumps that the electrical connections were reversed and the compressors were running backwards. So a lot of little things can be revealed from simple testing. So anyways,
you think that's what this is reading?
See, I think we've got some cross-contamination here.
Away from the thermostat.
So, assuming the above ground issues have been identified and dealt with, the ground loop is determined to be part or all the problem. What we want to do is rebuild the loop parameters as installed. And try to use the original hourly loads if they exist or rebuild them. If the inputs are realistic, the simulation should determine if the entering water temperature range is acceptable for the mechanical system. If the, excuse me just a second. I'm sorry, I'm on a meeting. My apologies. Let's see, so what we're doing is we're rebuilding, we're trying to simulate assuming we have a problem with the ground loop, we're going to rebuild the loop parameters as they were installed with GLD. We're going to use the original hourly load simulation if it exists and the heat pump schedule for inputs into GLD. And if the inputs are realistic, that simulation using GLD, and if we've got the thermal conductivity test parameters as well, we should know if that loop design is acceptable or not. If we find that the entering water temperature range is outside of the acceptable limits, and we believe the inputs are valid, adding the more capacity in the form of digital heat exchanger, adding in a hybrid component or other strategy might be considered. Or what we have found too, that sometimes we can reduce loads by better control of outside air, improve the lighting to reduce internal gains, that sort of thing. So we're going to go walk through the first example. And hopefully I've whited out all of the identifiers, so I'm not revealing. This is an actual problematic system. So what we don't want to do is identify the problem publicly, because this job is still in litigation. So this school is in the Rocky Mountain region. The system never worked from the first day of operation. We used the original loads, heat pump schedule, and install parameters. It does have a horizontal ground loop, so we reconstructed the horizontal ground loop. There was no TC test for the horizontal loop field, so we interpreted the thermal conductivity values from a geotechnical report. And then we did determine the ground loop was severely undersized, and it did use a central plant that we identified as a problem right from the get-go, because one, the chiller was never designed or intended for extended range operation, and the design called for 140-degree leaving water temperature to baseboard, which, as most of you know that have dealt with ground source heat pump systems, you've got to design the delivery system to match the capability of your plant or your heat pumps. So we also had a bad sequence of operation, and to make matters worse, the general contractor and his mechanical decided to value engineer an already questionable design. So this thing went bad to worse. So now I've got a lot of feedback. Here. There, that's better. So this is the ground heat exchanger installed. Let me get this down a little bit.
Terry, I think if you mute all the new participants, if there are any left to mute, it may help.
Okay. I appreciate that.
Okay, I just got muted.
Okay, so the ground exchanger is installed. We had 130 slinkies loose. And the installation depth was 10 foot below grade. So what we did was we rebuilt this system to see where it might be with the current loads, and we couldn't even make the simulation work for the original load calculation. So we knew we had an issue with ground loop, along with a lot of other things. So what we did was we looked at the loads, and we noted that the gains were pretty excessive, and a lot of schools are cooling dominant. But in this location and with the architecture, it was our sense that the cooling loads were way out of whack on this thing. And sure enough, when we summarized it into a monthly format, you'll notice, let's see if I can get the pointer. It's not really, I hope you guys can see this, but one of the revealing things, and you can also pull this on your load summary from GLD, we noticed that we had an annual equivalent full load hours and cooling of over 2,000 hours. And this is a semester school that the outside design temperature is 10 below zero, and it's not going to be operating in the summer. So when we looked at also the total cooling and for the annual loads, It's substantially higher than the total heating load, so we knew we had an issue with the load profile. So we ran the load, the 8760 hourly loads, and we determined the facility to be much more heating dominant instead of cooling dominant. We had a -10° outside design temperature and 78 degrees outside design temperature for summer. It's a semester schedule, as I noted earlier, and we had very little or no occupancy during the summer. So after we reran the loads, the new loads with GLD, and then we also looked at the thermal conductivity we interpreted from the geotechnical report, we felt like the loop might have worked had we used heat pumps that were intended to be used on a closed loop operation, for extended range. The chiller that was installed was certainly not be able to tolerate 35 degrees entering water temperature and produce 140 degrees leaving. So we knew we had a problem there as well. So with the updated load profile now in a monthly summary, and this is from GLD, our new full annual equivalent full load hours for cooling is 589 versus 450 for heating. And if you'll notice, the original full load hours was over 2,000 for cooling and under, well, no more than 220 for heating. So there's quite a bit of difference on the load calculations. And we believe the latter is to be more realistic. We ran several reality checks and actually called in another engineer for peer review on the load calculations just to verify and validate. So, summary of problems. It had a flawed basis of design, flawed load calculation, sequence of operation was very problematic. The central chiller plant was not made for this application. The delivery system was also incompatible for the application, and the ground loop design was problematic as well. And if you'll recall, everything started with loads, so this is another reason why a good load calculation is the basis for anything you do with a ground source heat pump design. If you've got a bad load calculation, everything else is going to be bad as well. So what were the resolutions? Well, we came up with several options. First one was replace the chiller with purpose-built extended range water-to-water heat pumps for a new heat pump plant central. Replace the delivery system with baseboard and fan coils and whatnot that would take a lower supply water temperature of, say, down to 110 degrees. Upgrade the controls and add additional ground loop capacity or a backup boiler. The client did not like that, though, because they're in a remote area. They wanted something simple to begin with. They also did not want to be paying for a lot of propane. So the option that they preferred that we offered was scrap the existing mechanical system, convert to a distributed packaged water-to-air heat pump system, simplify the controls, and decouple the ground loop. And then they ended up wanting to go with a brand new vertical loop field. We did recommend staying with a boiler for outside air makeup, and they did accept that. So once all the negotiations get done, they'll decide which option they're going with. So let's move on to example 2. This is an office facility. It is new construction. The system was working, and this is in the Northern Rockies. That's about all the information I want to give you. Don't want to be liable here. But the facility has a very high operating cost, very high maintenance, and a lot of comfort complaints by the occupants. This system also had a central water-to-water heat pump plant, but unlike the previous example, This system used purpose-built heat pumps for extended range, so they were compatible for the purpose. They did service a VAV system, and they did have the right low temperature delivery system. That everything was spec'd for 115 degrees supply water temperature, which was okay for the water-to-water heat pumps. They had a vertical groundlet, 35 holes, all tied together on one header pair, so that was a red flag right to begin with. One of the high operating cost features we identified immediately was about a 20 horsepower ground loop circulation pump, and there was no VFD on it. We estimated, because no one could provide hourly loads, so until we get those loads, we just did an estimate using design day loads, and I'll show this in a moment, that maybe the loop is sufficient, but we can't tell for certain. We do suspect from some of the paper trail that the loop was designed using a peak load only, using residential loop design software, so it's not accounting for the internal gains of commercial building. And the other issue we identified off the bat was the sequence of operation had the entire heat pump plant either in cooling or heating only, with over 25 independent zones in the facility. So either the entire building was cooling or the entire building was heating. So very few people were happy unless they controlled the thermostat. So earlier, the client had hired a consultant to determine where the problems were with the system. And he claimed the ground loop was doing great in the winter because he had a consistent 58 degrees entering water temperature to the heat pump plant. And our comment when we saw that was, well, yeah, that's 58 degrees because he's not getting any heat exchange in it, so he's not using the ground loop. So there were also a lot of complaints on comfort that everyone was ignoring, and the original consultant that was hired couldn't even figure out that the system was cooling or heating only. So they had a lot of issues with their first consultant. So we rebuilt the loads as best we could without doing a full 8760 hourly, assumed 750 full load hours for cooling and 1500 for heating. And using GLD, we decided that, well, the ground loop might actually have enough, we had 35 holes, 300 foot deep, and we felt that the ground loop could potentially work. They also had a TC test, so we had everything we needed to recalculate the loop field except the hourly loads that we suspect were never generated. But we did have a TC test and we had a heat pump schedule, so that was good. So we think that the loop field might actually work. But we did have one problem with the loop field. If you'll notice, we have a single header pair servicing all 35 holes. And what that resulted using, and you can use GLD to do this. GLD will do a pressure drop calculation. And at peak flow, we were at 234 GPM at 96 feet ahead. And what's nearly as ugly, or actually worse, is the purge rate to hit 2 foot per second velocity to get air out of the system would need 232 GPM at 422 feet ahead. So this is pretty substantial. And we did note, even though they had air separators, that air was still inhabiting the system, and the air vents were continuing to work after, I don't know, a couple of years. So this was a definite issue. So one of our recommendations was to go back in, leave the ground loops in place, but re-header and to a lower pressure drop. And the recommendations we came up with would reduce the pressure drop from 96 feet ahead to 33 feet ahead. So that would have been a substantial reduction in pumping costs. And then, of course, the purge rate would have dropped 53 feet ahead at only 46 GPM instead of 232 GPM at 422 feet per head. So now you could actually purge each individual header pair if it were headed in this configuration with a residential purge pump. Wouldn't have been hard at all to do. So the summary of the problems for example 2 had a flawed basis of design. We still don't know if we had a load calculation. Sequence of operation was not good. We're still not convinced that the ground loop has the capacity to handle the system the way it should. Can only determine that. Headering configuration was we determined was one of the biggest reasons of the high operating costs, coupled with the pumping that was not using a VFD to control it. So our solutions were repipe the heat pumps internally to permit simultaneous cooling and heating, which would also encourage load sharing and further reduce operating costs. Update the sequence of operation to be compatible simultaneous cooling and heating. Generate an hourly load profile. Rerun the ground loop simulation to determine if we had sufficient ground loop or not, and then reheader the existing loop field and utilize VFD pumping control on the ground loop. So let's move on to example 3. This was also an office facility, new construction addition. We had very problematic or questionable construction documents. It was a peak load only on a commercial facility. The mechanical plans actually referenced 200 foot per heat pump ton for the so-called loop design. Loop field details, manifolding schedule, etc., were noted to be determined by driller. As you guys, there's some drillers that can design loop fields, but most of them are mechanics, and they haven't been trained for this. We had 38 nominal tons of water-to-air heat pumps, so this is not a real big facility. Without doing a pressure drop calculation, we had about a 10 horsepower circulation pump on this thing, and we felt that that was probably excessively high for the size of the system. And instead of extended range, we had a mix of extended range and closed loop parameters on the heat pump schedule. So we kind of had some suspicions on some other parts of the design. Luckily, this was before construction, so we were actually doing forensics on paper before we got to a problematic installation. So the general contractor had actually worked with us before, and he started asking questions, wasn't getting answers. So he started raising red flags and brought in several folks to review the design documents. So we ran a new hourly load profile, came up with what we felt like was a reasonable load calculation, and this is right off of GLD's zone manager, so it's the monthly summary for the hourly loads. We also looked at the loop field layout by the driller who had designed this with 200 foot per ton, and we had 4 header pairs with 8 circuits and 1 header pair with 6 circuits. And so we didn't like that. Things were not balanced out very well. The driller experience was with residential only, so he had no design training for commercial. Just was not aware of what he needed to know. So what we did was we used GLD to take the driller's layout, and that is actually it doesn't really show the symmetry on the spacing that well, but let's see if we can go back to previous. We're supposed to be on 15-foot spacing between each header pair and each ground loop. So it doesn't appear to be scale, but if you'll notice on the scale X and Y here, we are appropriate. It just doesn't appear that way on the plot. So we ran it with the hourly loads, and actually this loop design probably would work. We looked at we had some adjacent TC test data in the area, so we thought this was pretty close. We still didn't like the geometry of the loop field, but had to admit that it probably would work just fine. So after playing with the system a little bit, using GLD, we came up with a 2x7 pattern with 20-foot spacing, and this time 400 foot deep instead of 200 foot deep, and we went to 1 1/4 inch instead of 3/4 inch pipe. And guess what? We now have about the same entering water temperature expectations, and we were also able to reduce the net footage of borehole installed. And notice this is 5,600 feet linear, and before we had 7,600 feet linear. So it's quite a reduction in vertical loop. So we looked at this thing, and others said, okay, we have an issue here. It looks like the loop is going to creep up in temperature. We know from experience that GLD and other loop simulation software for vertical loops, this is really not realistic. If your loop is going to overheat, you're going to know it in the first year or two. This is a problem we have with simulation software, because it only accounts for the perimeter of soil to the furthest limits of your loop field. So it's not looking at the dissipation capability of the loop field. Same thing on a heating dominated load, where this can inverse and says, say maybe in 10 years you're going to freeze up the loop field. If it's going to work in the first year or two, it's going to work, period. So on this project, for the redesign, we reselected heat pumps for 85 degrees entering water temperature for cooling and 35 for heating. We updated the sequence of operation and simplified it, reduced the loop field to 14 holes by 400 foot with a $31,000 savings. And we also lowered the pressure drop both for operational use and for purging, and went down from a 10 horsepower pump to, I think, 2.5 or 3 horsepower with VFD control, and we've further decoupled that to improve load sharing and further reduce operating costs. And I think I got some of my slides mixed up, and I apologize. This goes back to the thermal creep we were talking about just a moment ago that was expected on the on example 3. And one of the reasons we know this is not an issue is this is from an actual job where we have trend data. This is a IKEA store in Denver, and we would have expected, if we believed the simulation results, that the loop would finally overheat, within a few years. And from actual trend data, we know that's not to be true. And every peak here is a 24-hour operating cycle. So in the evenings, as soon as we relax heat gain on that loop, the temperature on that loop is dropping. The blue is entering water temperature from the loop field, and the red is return water temperature to the ground loop. So you can tell that that ground heat exchanger is accepting a lot of heat and dissipating it fairly rapidly. So I'd like to conclude and then open up for questions if you guys have any. Each forensic evaluation will be different. Always look for the simplest issues first, because that's where they really most time are. But one thing to remember on a ground source heat pump installation, if you have one issue somewhere, it may cause a cascade effect and make other problems with the rest of the system. So a lot of times you'll find symptoms, but you have to find the root cause of those systems. A lot of due diligence is involved. We start out when we do due diligence on a forensic project to look at the all the paper first before we make a site visit, trying to get familiar with everything as much as we can and improve our due diligence before we get out on site to confirm things. Again, be prepared to spend some time on site, work with the building automation system if it has it, a lot of visual inspections. We also will test various components. A lot of times either because information does not exist or the responsible parties don't want to share the information because they're afraid of litigation, you have to start from scratch. But GLD, just like to finish up, that it can be your anchor point in resolving a lot of these issues. It allows you to test your concepts or your what you suspect might be issues based on loads, heat pump schedule, and that sort of thing. All right. I know that I've gone through this fairly quickly, but would like to open up for any questions.
A question here from Richard Lay.
Yes, sir.
Do you have a profile of problematic loop arrangements? And for example, do you see proportionally more problems with horizontal loops than vertical, or within the horizontals, do you see more problems with blinkies versus serpentine? Do you have any feelings about the riskiness of shallow versus deeply buried horizontal loops?
Actually, what I see is if the horizontal systems that have been a problem have been as a result of the same problems for vertical. A lot of times people don't know how to run a thermal conductivity test for a horizontal loop. They rely on assumptions, and it's the same kind of problems for horizontal. So I wouldn't say that one configuration is more susceptible to problem than another. It's really dependent on the due diligence of the original designer.
Okay. All right, thank you. Well, second question from Richard Lay here.
Okay.
Any assumptions or conclusions about whether loops tend to underperform in cooling versus in heating? A lot of the publications, like Steve Kavanaugh's work, is for cooling-dominated systems in the south, and I don't see the same sort of articles from northern geographic locations like you're reporting on here from Rocky Mountains. Do you have a feel about?
Yeah, we see the similar results for heating dominated and for cooling dominated. In fact, I just got back from last week. I was in South Texas on about a 70,000 square foot facility that is definitely cooling dominant, and it started out with just like what we find with a lot of heating dominant commercial and institutional jobs. Controls were not properly designed, the bad sequence of operation, and the loop system was short on it as well. So that system was overheating. We've already resolved some of it by they had the economizers on the enthalpy wheel units. They were open 24/7, so they were trying to cool the whole county at one time. And we've seen the same thing on heating dominated, like schools and whatnot, where they're bringing in outside air 24/7. So your closed ground loop, whether it's vertical, horizontal, or whatever, they're not designed to heat or cool the county. They're just for that envelope. So I'd really have to say, in answer to your question, we see the same cause and effect, whether it's cooling or heating dominated.
Okay, thank you.
Terry, Jacob here. I had a quick question. This might be a tough one for you to answer, but in general, have you seen more or less, or I guess do you recommend a certain manufacturer of heat pumps versus the other, some that you would definitely recommend as the best ones, or some that you've seen that are actually a problem?
Oh, very good question. And yeah, I actually do have a good answer to that. I think what you want to look is the submittal data from the manufacturer and verify that you have a good performance table starting out at a low entering water temperature at 20 or 25 degrees, going all the way to 110 or 120 degrees, and be really careful about heat pump manufacturers that, and we have a lot of problem with a lot of chiller manufacturers. When we ask for submittal data from a chiller manufacturer at enough entering water temperature points and cooling and heating so you can build a heat pump library for GLD, when we can't get that data from that manufacturer, we don't want to use that product.
Right.
We've actually had some chiller manufacturers say, well, just put in more ground loop. You know, really kind of a sloppy response to my question. And I said, well, you don't understand. To model a ground loop, we'd have to know the efficiencies of your product at certain conditions. Otherwise, the software can't map the performance of the loop field to predict how it will work. So I guess it's not brand dependent. It's really dependent on the manufacturer if they can provide sufficient submittal data. There's another advantage to that. If you have published data from that manufacturer, the liability for performance of that product is back on the manufacturer. And I think a lot of these guys realize that, so that's why a lot of them suggest, well, you always need to put in a backup cooling tower or a boiler. And, you know, I run into that a lot with these guys, and I say, no, we shouldn't have to if we design the loop correctly. But we need your help, Mr. Manufacturer, in having good performance data to use.
Right, so you haven't had any particular issues with, say, I'm just throwing out names, but let's say McQuay heat pumps versus Water Furnace or Climate Master.
No, I haven't had a real issue with any of those products. And I will say this, some products are less efficient. Let's say it's a commercial job and it's a cooling dominant job. I would probably favor a heat pump product that has a higher efficiency in EER at warmer entering water temperatures, so you'll have less compressor energy to deal with in your ground loop.
Yeah.
So that could preclude some manufacturers that have kind of a, say maybe only have a single speed compressor product line versus those manufacturers that have a 2-speed compressor line.
For sure. I guess I was trying to put you in a tough spot and actually get you to recommend your favorite heat pumps.
Not in a public forum. Someone will probably lock and load their gun for me.
Fair enough.
Well, I'd like to ask the audience a question. We're going to have a follow-up GLD presentation on December 3rd where we're actually going to use an example, maybe 2 to time permits, on using GLD through an actual forensic evaluation. And I've got several examples, but if anyone in the audience has a specific project that they would like to look at, I would love to bring that in, and we can work with GLD on the project. If you know you have a loop field that's probably insufficient or something along those lines, And what I would ask you to do is maybe drop us an email through thermal dynamics, and we can discuss that before the December 3rd webinar.
Who do we direct that to? What person?
Jeff Walton.
Okay.
And I have a new email address. We have a new email system coming our way. Otherwise, I'd give you my email address right now. But I think I've got the attendance list from Jeff Walton with Thermal Dynamics, and maybe I can just send a spam out. And so if anyone has any suggestions for a forensic evaluation, we'd like to consider that. We don't want any specifics that can, make anyone uncomfortable. That's all. So we want it, names and locations. We want them whited out.
And not just having a general communication that are being allowed to say
It sounded like someone else was trying to ask a question, and it's kind of fuzzy. I can't. I apologize if I can't hear anyone.
I hear that background. This is Richard Lay again. I hear the background talk, and I can't decipher. I do have one last question. Have you detected any faults that are related to the grouting of the borehole? Or are you able to discern that in your forensic?
Yes, as a matter of fact, we had a project here recently that the loop seemed to be running warmer than it should, and we had some photos of the job as it went in, and something didn't look right on the grouting procedure. So we picked a few ground loop locations and excavated, and sure enough, we found that some of the boreholes on this particular project, there was no grout in the holes. It had all dropped away. They had not mixed the grout properly. They had not trimmed it all the way from bottom to top. And because when we ran the simulations, we said, no, this loop field should work, and we believed it should have. And the engineer had actually done a nice job, but there was no quality assurance for the loop field during or contract administration during installation. And anyways, they got bit by the contractor.
Thank you.
Mm-hmm. Yeah, that's a very good example of using GLD to, rebuild the loop design and say, well, if it should not, and that led us back to the grouting issue.
Okay.
Any more questions? Well, let me at least give you guys my phone number and my current email address. It's our office number here is 303-424-1622. And my current email address, if you have any questions, it is going to be changing shortly, but right now it's loopman, LOOPMAN at majorgeothermal.com. So if anyone does have any examples that'd like to have on our December 3rd webinar, we'd sure like to take a look at it.
Thank you, Terry.
All right, guys.
We'll post the recording within a couple of days, and I'll send out a message to everyone that had signed up for this webinar.
Excellent.
Okay.
Well, if there's no more questions, I guess we'll call it good for the day. We really appreciate your participation, all.
I guess this is a legit question. What is the condition?
It's the question for all of them. The question is, do you trust the engineering company that they did their due diligence as a professional engineers, or do you think they're all bullshitters and you don't want to ask the question?
I guess I was worried that, oh, if it doesn't perform, looks like it's
Like every single energy efficiency project that I hear has exactly the same question. Do you trust the engineering company to do their design?
Sure.
Or if you don't trust them, then don't pay for anything.
If there's no more questions, I guess we'll close it down. I do appreciate everyone's participation. And if we have any questions,
I have just one short question.
Sure.
I'm wondering if you recommend any book or literature for the academic point of view.
I'm sorry, I didn't catch that last part, sir.
I'm wondering if you recommend any book or any literature for the academic point of view to read this ground loop design.
Yeah, Dr. Kavanaugh and Dr. Rafferty's commercial ground loop design manual from ASHRAE. We're supposed to have an updated edition to that. I don't know if it's been published yet, but I know at the ASHRAE conference in Seattle, the target date for release for the new commercial design manual from ASHRAE was supposed to be released here before the end of this year, either this month or next month, and I don't know if it has or not, but it'll be the original manual is titled Ground Source Heat Pumps, Design of Geothermal Systems for Commercial and Institutional Buildings, and it's authored by Dr. Stephen Kavanaugh and Kevin Rafferty. Okay. And that's I don't know, let's see what the original date, I'm looking at it right now, when it was actually published, oh gosh, back in 1997. And I still use this manual. It is not only for design, but forensics. It's a great reference manual just on the basics and fundamentals and what to consider on a commercial scope ground source heat pump system.
Okay, thank you.
Mm-hmm. Any more questions? Well, I guess we will call it good. We're about the end of our hour, but we will look forward to talking to the rest of you guys on December 3rd, and hopefully you can join us. And again, if anyone has any examples they'd like for us to work through for forensics, we'd sure like to take a crack at it. So please get in touch with us, either Jeff with Thermal Dynamics or myself, and we'll go from there. But I wish everyone a good rest of the day. Appreciate it.
The one that I would do is So